This is an addendum to the fourth lecture of the series I'm giving on characteristic classes for my class at the University of Oregon and others who care to follow along. It's an addendum because if you watched that lecture, presumably you realize that I was giving a proof and saw an issue with it. And I guess I could re-record, but there's something to be said for the practice of mathematics being more visible. A lot of the most wonderful theorems of the 20th and 21st centuries, I'm sure before that, there were mistakes that people made. You know, Thom thought that that any homology class was represented by a submanifold. In fact, I'm kind of will soon, the next lecture, introduce Thom cochains to in part because of that mistake. You know, Quillen was doing some calculations and calculating characteristic classes of tensor products of vector bundles and getting wrong answers, and that led to his realization of the connection between algebraic topology and algebraic number theory and formal group laws. So anyways, my mistake, I think, is a lot more pedestrian. I don't think this is going to lead anywhere, but I wanted to just leave that lecture up there and correct my mistake today. And especially, you know, we're at an interesting time. This probably will be a bit of a turning point in how math is disseminated because of the pandemic of 2020. I don't know when you might be listening to this, but yes, this is an interesting year in which we're moving some content and meetings and things online. And of course, I think math in person has a lot to be said for it. But in any case, in this day and age, one thing I think mathematicians need to be clear about with scientists more broadly as well, that the process of doing good math, the process of doing good science involves you know, inspecting your own thinking and acknowledging mistakes and then working to understand them and find clarity. And yeah, so this is a very 2020 kind of lecture in that, well, more aspirational. What we need more of is people sort of being clear about what they know and don't know, and willing to kind of look at their thinking. Okay, so so right above here we have this not the exercise, but this. Let me make this smaller as I usually do for the projecting board. I wanted to take this sum of partitions of unity, sum over a partition of unity of bundle isomorphisms in order to make a bundle isomorphism, but that in fact is bad. So let me clear that up first. What got my thinking? So here's a non-theorem. All vector bundles are isomorphic to each other and thus trivial. Here's the non-proof. We may, you know, subdivide, you know, refine the covers so that, you know, E and E prime are trivial over the same open sets. We, of course, once they're both trivial on the same open set, we can define those isomorphisms locally and then use a partition of unity to glue them together. So, so maybe we're over a pair compact, or in particular compact base. So what goes wrong with this? Well, I mean, it helps to maybe think about the simplest example. So if I've got the Mobius bundle versus the trivial, actually, let me use colors. So for the Mobius bundle, maybe I glue the interval cross R with 1 here and -1 up here, whereas with the trivial, I glue them with 1 here and 1 here. And so then these isomorphisms, once I, so then the isomorphisms that I would be using, once I take a partition of unity and add them together, if I got to sort of the point 1/2, 1/2, at this end, what we would see is eventually the map becoming 0. So, I mean, what is true, you can use this argument to make a vector bundle map. As we've discussed before, the vector bundle maps are maybe not so nice because their ranks jump, and that's exactly what happens here. So it is true that all vector bundles, I can get a map from one to the other. That's actually much easier. The 0 map works perfectly well. You can say maybe one that's sort of rank, full rank, except on the codimension, positive codimension set or something like that. That also, there's other arguments to make. So this idea of getting our trivializations, using them to make vector bundle isomorphisms and gluing them together with a partition of unity was not the right idea. Sorry about that. That's what happens. So what I did is I went to Hatcher's text vector bundles and K-theory and went ahead and let's adapt that. So let me let's recall the setup. I'm going to change variable names just a little bit. So what we have is our vector bundle E is trivialized on these UI cross, let's just call them AB for some interval within the interval 0, 1. We were calling that T minus epsilon to T plus epsilon, but just some AB. And we used a little compactness to get ourselves there. Hatcher sets it up. I'm sort of slicing the X cross I along X slices. Hatcher sort of gets to the same place basically, but it just a slightly different setup. And what we want to show, oops. We want to show that E restricted to X cross A is isomorphic to E restricted to X cross B. So we have our partition of unity, Fi. For our cover UI, which remember is finite. And what we're going to do, let me draw it first. So really we want to, so here's X cross A, and this whole thing is X cross AB, like that. We've got our open covers, U1, U2, etc. And we want to show we're isomorphic at the ends. Well, the first thing you might do is say, all right, well, let's try to find a little amount that we can be isomorphic. Of course, a subinterval within an interval is another interval. So if we could do that, we would basically be done. So that's also that's a naive guess for how the argument goes. That yeah, that that is pretty quick to say, well, nothing like that will work. But then what we're going to do is we're going to sort of push across. At some point, we have to use the geometry of the interval. We have to push across. And what I'm going to do is use a bunch of spaces. I've got x cross 0, x cross 1. I'm going to define I'll call it x sub I to be the graph of the function that is, I'm going to look at the sum of from say j equals 1 to I of f sub j. And that's the progress I'm making. I'm just going to then, I'm going to start with the value a and end with the value b, and I'm going to interpolate using the functions, the partial sums from of these partition of unity functions. So that means that x0 is x cross 0, and xm is x cross, or sorry, a, and xm is x cross b. So these interpolate. Each is a graph, so each xi I can project onto xi minus 1, because, well, let's even take the next one. So what is x2 going to look like? It's also going to be down at x cross a for most of it, and then it will start rising here. And the point is, because the fi are positive, each one sits above the previous, and so there's a projection because they're graph. There's a unique, call it t value for every point in x, and I can just project down, and each of these is homeomorphic to x. And maybe we need some point set topology on x to have good graphs, but we're definitely in that kind of setting. So each of these projects onto the previous, and I'm going to call that pi. And each of these is a homeomorphism all the way down into x cross a, which is x0. So those are all homeomorphisms. And so then the claim is that the main claim, which finishes the proof actually, is that E restricted to xi is isomorphic to E restricted to xi minus 1. And what we have to do is just get a full rank map on every fiber. And now what we're going to do is, I'll just give it to you. So, I mean, the idea is, well, first I'll tell you the idea. The idea is that since we're in this, since the only places where these differ are within UI, that then means that, so here we're within U1, the bundle is trivial there, and so we can actually use the bundle, the identification as a trivial bundle to identify fibers. That's it. And it's just a matter of using that and using a partition of unity, but also using the geometry of the interval to sort of push across a piece of X over which now the bundle restricts isomorphically, again, as opposed to trying to take some combination. So let me write this out and then we'll be done. The map that we're going to do, well, any point in the bundle, and this is for X in UI, for X not in UI, you note that Xi equals Xi minus 1. So, so that's fine. They're obviously isomorphic. And for X in UI, I'm going to send some point xv, and this is really, if you will, x comma graph of X within this interval, but I'll omit those two. Oh, well, no, so X is in this graph. Two, well, I'm going to apply PI. Those are these homeomorphisms that go from one graph down to the next. And then I'm going to use a trivialization to identify them. If you want in full coordinates, that's taking the trivialization homeomorphism. So that's taking the U cross or UI cross Rn and identifying it with the pre-image of U under the bundle map. So that's, and I'm going to take the inverse of that on V. So V is just some element over X. By taking the inverse, that means I'm going from the actual bundle to the trivialized version, UI cross Rn. In UI cross Rn, I can then just take PI cross the identity on Rn, and that's now moving which fiber I'm in. And now I'm going to apply phi UI, and now I'm in the right fiber, and I'm now in the vector bundle E again, as opposed to a trivial bundle that's off on the side. And that does it. And it's pretty simple to check that that's an isomorphism on all the fibers, preserves linear structure, and all that. And so that is the desired isomorphism. And we get it one at a time. So eventually X0, which is X cross A, has the same bundle over it as XM, which is X cross B. All right. I will shortly start the next lecture, which is a shift of topic. We're going to start setting up some of the machinery that I prefer to do cochains with. So see you soon.